Good morning, class. Or afternoon, I guess. Depends on when you're watching this. Today we're going to look at surface integrals in both the implicit and parametric forms. We just did surface area of shapes. Now we're going to look at evaluating a function over a surface. To do that, they're used to compute quantities such as the flow of liquid across a membrane or upward force in a falling parachute. A bunch of different reasons for doing surface integrals. So basically, it's the same formula that we did the last video when we did implicit, except for now there's a new function here. So we're just calling this function g of x, xyz I should say. So here's our formula. Again, pause the screen if you need to write. Again, the form is d sigma can be represented as all of this, so it's basically g d sigma. Integrating over surface of cube or other rigid shapes can be found by the sum of the integrals over each face. So let's look at a problem with that. So again, if you need to write, pause the screen and then we're going to go on. Okay. So we're integrating the function xyz over the surface of the cube cut from the first octant by the planes x equals 1, y equals 1, and z equals 1. So we only want those three sides. So in order to do that, technically, to evaluate the surface integral over the cube, we would normally, of xyz, d sigma, we would normally have to do, side A of the same thing, and then plus ... do B and C. So let's just look at side A, for example. Let's do side A. So here's the surface. So for side A, we have a few things. We have, basically the function is that the surface function is z equals 1, because it's a plane z equals 1. Therefore, that's the surface, and then the shadow region will have a bounds of 0 to 1 for x and 0 to 1 for y. Okay? So now we have to get the rest of our information to set this problem up. So it's like what we did with implicit before. The p vector, or the normal vector to the shadow region, is going to be 0, 0, 1 because I chose the top piece. If I chose another piece, it would be the whatever direction it's perpendicular in. But we're going to do this one. The gradient of f, so this is f right here, by the way, is the surface. So the gradient of that is just, again, 0, 0, 1. It's actually the same thing as the shadow region. If you do the dot product of that and take the absolute value, you get the absolute value of the gradient of f dotted with p is 1. And you get that the magnitude of the gradient of f is 1. So this is kind of a nice problem. So our d sigma is 1 over 1 dA, which in this case is going to be dx dy. So now we're going to set up our actual integral. So to do side A, if we integrate this surface integral, we get that x goes from 0 to 1, y goes from 0 to 1, of the function x, y, and then remember, for this surface, z is a constant 1. So I can put a 1 in there, and that's how you get rid of the z here. It becomes a 1. And then we put our d sigma in, which is just 1 over 1 dx dy. So basically, all it is xy dx dy from 0 to 1. So we integrate this. I'm going to do x first. I get x squared over 2 times y, value from 0 to 1, which is 1/2, and there should be a dy, which is a 1/2 integral from 0 to 1 of y dy, which is a 1/4. Well, that'll just become 1/4. Now, just looking at this shape, since everything is 1, and even though we're changing the direction of the vectors, side B and C will be the same in this case due to symmetry because of the function. The function is just x, y, z. So if I change the function, x and z would be 0 to 1, and y would be 1. If I chose the plane side C or side B, x would be 1, and y and z would go from 0 to 1. So therefore, side B and C will be the same, so the total answer, or total integral, that's a weird way to say it, sorry. I'm going with it. Would be 3/4. It's It's one of those days. Because it's side A plus side B plus side C would give me this, because side A is 1/4. Okay? So the only new thing is you get an extra function, which can cause difficulties because you have to usually get it in 2 variables. Alright, I have time for one more section. It's, again, similar. We're going to talk about flux. Alright, again, if I'm going too fast, I have to go fast because I only get 15 minutes per video. And so if you gotta pause, you gotta pause. And that's fine. Alright, the last thing we're going to talk about today is flux. So again, we talked about flux before. If F, again, is our vector field or velocity field, we had F before we were dealing with Green's theorem. It's in 3D fluid flow. Flux across the surface is the net rate at which fluid is crossing that surface. And it's given by this formula here. It's basically the velocity field dotted with the normal vector and then d sigma. Well, d sigma is the same. So here's the thing you have to worry about. To use this, we need n, the normal vector. Well, the normal vector, it's a unit vector, I should say. It's the normal unit vector. So it's the gradient, and we call this g now, even though this was our old little f. They changed the letters because there's now a big F in the equation. If you want, you can pretend that this is little f, and then put little f's in all of this. It's fine. It doesn't matter. It's just I think the book changed it because there's a big F now in the equation. So when you plug in, so you could either, this is like the simplified version right here, or you can go back to this version right here, where we know you'll be given F, you'll have to find the normal vector, and then d sigma is still the magnitude over the, the dot product, all that fun stuff. All right, that we've been dealing with so far. Yeah, the magnitude of F over the dot product of the gradient of F dot P. So that still stays the same. So let's try one of these problems. First thing we have to do is probably get it to 2 dimensions. Let's see what we got. We've got that, where is our surface? Our surface is this cylinder, right? So that's my little f. Or if in the problem up above, you could call it little g. Now it looks like I wrote 4. I'm going to just keep using little f. You guys will know big F is the field, little f is the surface, okay? Because I know they changed it to g up there, and you know what, let's just use little f. So, we get that little f is equal to y squared plus z squared equals the constant. We don't care about that part. That means the gradient of little f is 0, 2y, and 2z. Again, looking at this diagram down here, this is the shape that we're dealing with. This rectangle is in the xy plane, so P is going to be 0, 0, 1, our favorite vector for P. Alright, so I have most everything. I also need to put in what big F is, just because. Big F is equal to 0, yz, and z squared. That's my field. That was just given to me up here. Be careful with the letters. There's no x component. Alright, so we have the field now. We have everything we need to start plugging in for this problem. So you can go up to... Oh, I didn't talk about this plus or minus, by the way. Whenever it's outward, it's positive. N is positive. And most of them will be positive, so I didn't really make a big deal about that, but I forgot to mention that. So you get to choose depending on which way you're doing it. If it's outward, make n positive. If it's inward, make n negative. So my point is, you can use this formula up here, or you can go back to the original formula that we had, just with all the pieces. All right? We know that d sigma is equal to the magnitude of f over the gradient of f dot p dA. So if we do that first, let's just do that. We get the magnitude of f is 4y squared plus 4z squared, which is actually a little bit more work. I didn't do this in my notes, but that's okay. So the gradient of f magnitude is the square root of 4y squared plus 4z squared. Now, you can factor out a 4, which is a 2, and then it's the square root of y squared plus z squared. But again, you know that this based on the problem, the surface is 1. So basically this magnitude is equal to 2. So this top thing is equal to 2. The bottom thing is little f, 2z, dotted with p, so it's 2z. So we get d sigma is 2 over 2z dA. So I've got one piece of my 3 pieces of here. N is just the gradient over the magnitude. So I'm going to change colors for N. N is just the gradient of f over its magnitude. So if I do the gradient of f, I have this vector. Divided by its magnitude, which we already found was 2. So N is the vector 0, y, z. And it's going to be positive because, again, we're outward. So now I have N and I have f. F is already given right here. So now we can set up this flux integral. I have f, and again, I'm doing this one up here. I'm doing all 3 pieces. You could have done a shortcut, and this is the simplified form, and then you wouldn't have had to find the magnitude. I'm showing you the long way because that's what we've been doing. So the integral then of the region, or of this, well, no, it'll be the region because we're going down to the shadow region now. So f dot n. So here's f, here's n. You get, multiply these together, you get y squared z plus z cubed. And then that's going to be multiplied by 1 over z dA. So when you do that, you get that the z's will cancel out. So I get the integral over the shadow region of the z will cancel there, y squared plus z squared dA. And again, since we know that for this surface, y squared plus z squared equals 1, we can just rewrite this as, this is just the region over the area. And then over here, if you look at the area, the shadow region goes from 0 to 1 here, and 0 or negative 1 to 1 here. So that area is just 2. So you get 2. So the flux for this problem is just equal to 2. Okay? I did it the long way. You could have done it the short way and just found the gradient of f and then the over the absolute value of the gradient of f dot p and not dealt with the magnitude. But I figured we'd do the old way just to show you all the pieces you can do. I like getting all the pieces, so. Alright, I'm sure I'll have a problem for you to try. I haven't figured out what that is yet, but, you know, I'm trying to break it down slowly because we have to get through May 8th, so I will do that for you guys. Alright, hope you guys are all doing well, and sorry this was kind of long. We are going to skip the shells, though. We're going to just go to parametric next, so have a good day.